Hi everyone. In the previous video, we had a look at graphing cubics that had been transformed from the base function to a transform state. In this video, we are going to have a look at graphing a cubic which has been written in intercept form. So, without further ado, let's have a look at the general shape of that. So we may or may not have a factor outside of the factorized expression, because that's what intercept form means, right? It means that the cubic has been factorized, fully factorized, as you can see here. So we may or may not have a number out here. And then we've got our three factors. Now, it's definitely a cubic because if we take just the leading x's here, x times x times x, we get an x cubed, right? And then we'll get possibly an x squared term, possibly an x term, and a constant term as well. Remember, constant term means a term without any variables in it at all. So all of those are a fair game if we expanded it, but in intercept form, it has already been factorized, as you can see. So let's have a look at an example. We'll get stuck straight into it. F of x equals -3 outside of x plus 1 times x minus 1 times x plus 4. So what I thought we might do is we might go through the usual steps to find critical points, but we're also going to utilize the concept of end behavior, which you saw in the first video on cubics. So we'll look at that again and put it into context for graphing this one. Okay, so number one, let's have a look at the x-intercepts. So the reason why I'm starting with x-intercepts is really simple. It's because it's the easiest thing to look at in this form. So the x-intercept is when we let y equal 0. So I'll stick the bit we don't know on the left-hand side. So -3 outside of x plus 1, x minus 1, and x plus 4 is equal to 0. Okay, so that's all good. So what are the x-intercepts? Well, using the null factor law, if this whole thing is equal to 0, it means that either this or this or this must be equal to 0 because they're all multiplied together. So one of them must be equal to 0. So that means, look, I'm not going to write down the full solutions here, but it means x plus 1 equals 0, which means x must be -1, or x minus 1 equals 0, which means that x must equal 1, or x plus 4 equals 0, which means that x equals -4. I hope it's okay that I don't write all that out. You should be familiar with this kind of concept already. So I'll just go straight to the solutions. So that means x equals -1, -1, 0 would be the coordinate. X equals +1, so 1, 0 is a coordinate, or x is equal to -4. So -4, 0 is a coordinate. So that's that part of it done. The next thing we'll look at is y-intercepts. And that's when we let x equal to 0. So in order to do this, we are simply, if you think about it, if x is 0, that becomes 1, that becomes -1, and that becomes 4. So effectively, you're multiplying the constant numbers together, keeping in mind that the operation here will affect the whole sign. So I go -3 times 1 is -3, -3 times -1 is +3, and +3 times 4 is 12. So that would be when x is 0, y is 12, like so. Okay, that's not too bad. Now, the third thing we're going to look at is end behavior. So what we are doing now is we're considering what happens when x is really, really, really big and negative. So really, really big and negative, or really, really big and positive. The way we express this is as x approaches negative infinity, and then all we're doing is we're considering the sign. We're not looking for a particular value, we're thinking about the sign. So the idea is that as x is really, really, really big, either a big negative number or a big small number, these parts of the function are negligible. All right, the sign here is important because when we multiply out numbers, negatives can change the sign, but effectively we're only interested in the x's. So we say something like this. This is negative. Negative times a negative is a positive. A positive times a negative is a negative. So this whole thing here would be negative when x is really big, and then multiply that by a negative, and we'll get a positive. So as x approaches negative infinity, y is positive. That's all we need to say. And as x approaches positive infinity, what does y approach? It is the opposite, but we just confirm it. So positive times a positive is a positive. Positive times a positive is another positive. So all of this is positive times a negative. Yep, we've got it. It's negative. Okay, so again, this is called end behavior. Okay, so what have we got? We have our x-intercepts. There's 3 of them. We have the y-intercept, and we know what's happening in our graph here. So when it comes to graphing it, which I think I'll do in this little corner of the woods, just so that it's all together, and I'll zoom up on it so you can sort of see it. So here's the graph here. So I'll draw my axes in. Oops. Label my axes, y and x. Okay, so step number 1, put all the intercepts in. So we've got x equals -1, x is equal to 1, and x is equal to -4. We've also got a y-intercept at 0, 12, so it's going to be up here somewhere. I'm definitely not drawing this to scale. So I've got my intercepts in, and now my end behavior becomes important because it says as x is equal to negative infinity, y is positive. So I know that this is x approaching negative infinity. So that means it's going to start up here somewhere. And then as x approaches positive infinity, y goes negative. So it's going to end down here. My graph needs to start up here and end down here. So now as I put the line in, I'm simply going to go up like this and turn up and down like so. And there's my graph. Looking a bit wonky there as usual for my graphing, but basically that's it. We're done. Now, you may think there's a critical point missing here. There are 2 critical points missing if you think about it. It's this one here, the turning point here, and the turning point here. How do I know it turns here, and how do I know it's turning here? Here's the answer. I don't. Well, not yet. When we do our calculus unit, we are able to precisely work out where turning points are in a cubic. But before we've done calculus, it's actually too tricky to determine what that turning point is exactly. So what we do is we kind of aim for about the middle and hope that's about right. Similarly with here. I mean, it may be that the turning point ends up being up on this side and then going down like that. I'll take a punt and set it over on this side and going down. I could be wrong, okay? But it's definitely not just in the middle. That you can't say that it's in the middle because it's not. It almost always isn't in the middle. So you just take a good guess. For this unit of work, as long as you've got it going in the right directions, like I've got here, then you'll be awarded full marks. After we've done calculus, you should be able to draw a bit more accurately. Okay, so that's that example there. Now, if we go over to Desmos, here's a little function I prepared earlier. So there's the base graph again, like so. Here's the one that we just worked out. And if I click on like so, you will see that the graph, I'll just zoom in probably a bit better, even though we can't see everything. There's a -4 there. There's -1 there. The function, the turning point is just after 12 there. So it is on the positive side like I had it, but only just. Zooming down to 1 there as I had it, and then going off like so. So yeah, my graph wasn't too bad, wasn't too shabby. Back we go. And that's basically how you graph from intercept form. Now I'm going to go through a second example just so you can see a slight difference here. Now this is still an intercept form in that the cubic has been factorized, but you can see I've got a repeating factor here. So if I expanded this, this would be 5 times x plus 1 times x plus 1 times x minus 2. So still 3 factors. I've got an x squared here times an x, which would give me my x cubed. So it's definitely a cubic, but we've only got 2 what we call distinct factors. So 3 factors, x plus 1, and x minus 2, but these 2 are the same, so we say there are 2 distinct factors. Okay, so what effect does that have on the graphing? So what we'll do is we'll go through the same kind of process and see what happens. So number 1, let's get the right color, x-intercept. I might just draw this a little bit smaller for space. So let y equal 0, so we would have x plus 1 all squared times x minus 2 is equal to 0. Null factor law comes into effect. X equals negative 1, negative 1, 0. Just point out what I mean by that. X plus 1 all squared would be equal to 0. Square root both sides to get x plus 1 equals 0, and then x equals negative 1. And then x equals 2 would be the other solution. So 2 comma 0. So x minus 2 equals 0. Therefore, x equals positive 2. So there's the x-intercepts. Moving on as usual to number 2, the y-intercepts. And we let x equals 0 for the y-intercepts. And so we have y equal to f of 0, which is equal to 0 plus 1 all squared times 0 minus 2. You don't really have to do this. You can use exactly the same. So I've forgotten the 5s there, but it doesn't make a difference there because there's a 5 there, as you can see. It doesn't make a difference because in the for the x-intercepts, I would just immediately divide out both sides by 5, and it would get rid of it because 0 divided by 5 is 0. And here it does make a difference though. So I didn't have to write this line. I could have simply gone multiply the numbers together, but do make sure you do remember to square the number inside here. In this case, it makes no difference, but 1 squared is 1, 5 times 1 is 5. 5 times minus 2 is negative 10. So we end up with negative 10 being the solution here, and I'll put over to the side here the coordinates, which is when x equals 0, y equals negative 10. Lovely. Now, endpoint behavior. The end behavior. So when x is negative infinity, approaches negative infinity, what's happening to our graph here? Let's have a look. So when x is negative and big here, the plus 1 doesn't matter, so we just worry about the x's. When x is really big, the plus 1 doesn't matter. So a really big negative number squared would be positive. A positive times a negative here would give me negative again, and so the whole thing is negative. So when x approaches negative infinity, y approaches negative infinity as well. Okay, and when x approaches positive infinity, well, we've got a positive squared is positive, times another positive is positive, times a positive, it's all positive. So we have that. So when we look at the graph now, I'll do the graph over here on the side. Got lots of space this time now that I've squished it down a bit. I'll draw my axes in. And I'll just skew the graph up a little bit like that, knowing what I'm about to draw. Label my axes as usual. Put in my intercepts as usual. So I'll do that in a different color so they stand out a bit. So we have negative 1 and 2 as our As our x-intercepts, we have 0, negative 10. Put it all the way down here. As our y-intercept. And now we need to consider the end behavior. And I'll just use a different color again, just so that we can make that stand out a bit. So as x approaches negative infinity, y approaches negative infinity. So it would be, it's got to start down here somewhere. And as x approaches infinity, y approaches infinity. So it means it's got to end up here somewhere. Okay, so if we were trying to do our usual thing of just doing turning points between the intercepts, you'd note that we would sort of, and then if I turned up again, it would have to have another intercept, which it doesn't. So that's a clear indication that this graph doesn't work as it stands. So the way it does work is like so. It has to go up to that x-intercept without turning. Then it's got to go to the negative 10 here. So it's got to go up, and then it's got to go down again before moving up to the 2, and then off it goes to infinity. So rather than cutting through at negative 1, it bounces at negative 1. So it goes up to negative 1 and then turns a sharp corner back down through the y-intercept and then back up through the x-intercept and then off to infinity. And beyond, if you like Toy Story. So that's the graph of a cubic where one of the factors is repeated. In other words, I've got a square there. It bounces at that particular intercept rather than cutting through it. So that's pretty much it. I mean, we can have a look at it on Desmos to sort of confirm that my graph looks okay. I'll turn off the other one. I'll turn them both off so you can sort of see it. So we'll zoom up on that one. So you can see from negative infinity, it goes up to 1, down to negative 10. My turning point was nowhere near as far down as this graph shows, but that's okay because we're not doing turning points yet. And then up it goes to 2 and to infinity and beyond. There you go. So that's basically it. That's how we graph from intercept form. Now, I've got a summary for you to help. You can copy it directly into your summary books if you prefer, or you can do your own summary. But this is basically it, the story so far. So if we've got the function in the form of a transformation, so f of x equals a outside of x minus h all cubed plus k, h could be 0, k could be 0, a can't be 0. Then we treat it as a transformation, and the inflection, so it gets to that point but keeps going, slows down when it gets to that point, but then it speeds up again after that point, but basically stays in the same direction. So kind of like this gets to the point and then goes up again, and the inflection is at hk. Okay, so if it is in the form of the two distinct factors, so one factor is repeated, like this here, then it bounces at that repeated factor rather than passing through it, and then it and then it passes through C. And finally, if the function is in the form that we've just looked at that first example, x minus b, x minus c, x minus d, then it passes through those 3 points and there's a turning point between each pair. There's a turning point between here and here, and there's a turning point between there and there. And I should say that for those two last forms, looking at the end behavior is really important. And that's it for this video. Thanks.